Hey Global Impact students, this is Mr. Ellinger. This lesson is on absolute value equations and inequalities. Our learning target for the lesson is to be able to solve equations and inequalities involving absolute value. Essential understanding: an equivalent pair of linear equations or inequalities can be used to represent absolute value equations and inequalities. Absolute value equations and inequalities can be solved by first isolating the absolute value expression, if necessary, then writing an equivalent pair of linear equations or inequalities. Some background. Absolute value is an example of a mathematical concept which cannot be defined using only one condition. The absolute value brackets in an equation or inequality are representative of two separate conditions. And we know this from previous lessons. When we first introduced absolute value, we know absolute value is distance on a number line from 0. And you can be on the left side of 0 in the negative direction, you can be on the right side of 0 in the positive direction, but either location, the distance is going to always be positive. So we have two conditions. We must identify the two conditions to be satisfied and write either a pair of equations or inequalities to represent those conditions. So in general, this is how this works. For an absolute value equation. To solve an equation in the form absolute value of capital A, where capital A is just some variable expression, that absolute value equals B, where B is greater than 0. What does that mean? B greater than 0. That means positive, right? Anytime you see this condition where a variable's got to be greater than 0, that means that that value has to be positive. And we know that distance is positive, so that's why that condition is put on there. What we're going to do is we're going to solve A, our variable expression, equals B, and we're going to solve A equaling negative. Now, where that comes from is there's actually a definition for absolute value, and we'll get into this more later, maybe in Algebra 2, where the absolute value of x is actually equal to x when x is greater than or equal to 0, and it equals negative x when x is less than 0. This is called a piecewise function, meaning this value, absolute value of x, is defined in two pieces. It's defined this way when x is a certain value, and it's defined this way when x is a certain value. So that's what kind of leads to these two expressions. So there is a reason why we do this, and it goes back to the definition of absolute value, which we haven't really looked at in an algebraic sense, but we will explore this more. Okay, so let's go ahead and use this. We want to solve the absolute value of n minus 5 equals negative 2. So the first thing we need to do is we need to isolate the absolute value. So we're going to add 5 to both sides of our equation. Okay, this gives us a 0 here, so the absolute value of n equals negative 2 plus 5 is 3. Alright, so we have our absolute value isolated. It equals a value of 3. So up here, what we're going to do is we're going to take our expression n, and we're going to set it equal to 3. And we're going to take our expression n, and we're going to set it equal to negative 3. We don't have anything else to do to solve because n is isolated in both cases. So these are our two solutions, 3 and negative 3. In our second example here, the absolute value is already isolated. So from here we can go ahead and apply this rule up here. So we'll take our expression 2x minus 5, set it equal to 13, and we will take our expression 2x minus 5 and set it equal to negative 13. Let's solve these equations. Add 5 to both sides. So that gives us 2x equals 18. Divide by 2, x is 9. Over here we're going to add 5 to both sides. 2x equals negative 13 plus 5 is negative 8. Divide by 2, x is negative 4. So we have solutions of 9 and negative 4. Now we can combine this back into one solution statement, x equals 9 and negative 4. Our third problem here, we need to first isolate the absolute value on one side, so we're going to add 5 to both sides. So this gets rid of our 5 essentially. So we have the absolute value of 3x minus 6 on the left equaling -2 on the right. Okay, so if we're not paying attention here, we just say, all right, I take the expression inside, set it equal to -2, and then I'll take the expression inside and set it equal to +2. And then I'll continue on and solve, and I'll get x equals whatever and x equals whatever. But like I said, if you are not paying attention to what you're doing, and you go from here to here, you've made a critical error. And what is that error? Well, the error is, if you go back to, again, think about the definition of absolute value, go back to our rule up here, b, this value over here has to be greater than 0. Here, our value is -2, that's less than 0. So what this statement is saying is that that the distance of this expression from 0 is -2. We know distance can't be negative. So this equation in this problem actually has no solution. So we have to be careful. Can't be in a hurry. We have to think about what we're doing. Okay, so we can write absolute value inequalities as compound inequalities. The graphs below show 2 absolute value inequalities. So the first one here on the left, we have the absolute value of some expression n minus 1 is less than 2. So what this is saying is that we have something here that's less than 2 units away. So here is our n minus 1. We're actually at 1, and all the solutions are going to be within 2 units, either left or right of that value. So we can take that and write that as a compound inequality as such right here. -2 less than n minus 1, which is less than 2. Okay, so when the distance is less than some value away, we know that all the solutions are going to be sandwiched inside of some interval, right? Now, contrary to that, if we look at the absolute value being greater than 2, that means we're at some point on the number line, and all the solutions to this are going to be more than 2 units away. Well, there are 2 different sides, if you will, to this that we can be 2 units away. We can either go to the right and from here on out be 2 units away, or we can go to the left here and go out to the left and be 2 units away. Right? So we got to understand, is our distance less than 2, so we're sandwiched in around a value, or is our distance greater than 2 or some value where we're going out away from our, our value or our expression? So these absolute value inequalities become AND problems, and these absolute value inequalities become OR problems. So that's what we're talking about here in this concept box. Okay, now if you go back to what I had written here earlier when I talked about the piecewise definition of absolute value, what we got to be careful on when we're solving these absolute value inequalities. Well, if I take my expression A, it's less than B, what I actually have to do, and they're kind of leaving this out here, is that I have to look at this and I have to look at this. Okay, and that goes back to the definition of absolute value. Here I'm fine. Positive expression less than B. Here I'm not fine. Okay, so think of A could be some expression like 2x minus 1, or it could be a quantity in parentheses, or it could be a simple variable like x or n or whatever. But we want to isolate that. So we don't want this here. So what happens is we divide through by a -1 to get the expression by itself. But when we divide through by a -1, we actually have to switch the inequality. So if you notice here, the inequality is reversed in both cases when we're considering the -b part of the definition. Okay, so here's an application problem. A food manufacturer makes 32-ounce boxes of pasta. Not every box weighs exactly 32 ounces. The allowable difference from the ideal weight is at most 0.05 ounces. Write and solve an absolute value inequality to find the range of allowable weights. They're making 32-ounce boxes of pasta, right? And it says that the allowable difference from the ideal weight is at most 0.05 ounces. So that means that we could be 0.05 ounces greater than 32, or we could be 0.05 ounces less than 32. So what's the range here? Well, our acceptable range of pasta boxes is between 31.95 ounces and what? 32.05 ounces. So this represents the situation here. The weight has to be between these two values, including those two values, in order to be acceptable. This is a compound inequality, but it is an and compound inequality. So it says write an absolute value inequality. So we're going to have some expression in here, and that expression is going to be less than or equal to 0.05. The distance from this is going to be 0.05, meaning we can go 0.05 above or to the right on a graph of this, and we can go 0.05 to the left on the graph or below this. So what is the expression that goes in here? Well, it's the difference in the weights, right? So let's say this box of pasta comes off the line, assembly line or the production line. We want to know how much different than the standard 32 ounces is it. So we have to take the weight of the box coming off the manufacturing line, subtract the ideal weight, see if the differences in those weights is less than or equal to 0.05. If this value is less than or equal to 0.05, then it's acceptable. If it's not, they're going to throw it out. If I remember, the way I would solve this is I could take the W minus 32 less than or equal to 0.05. I could take the negative of that, W minus 32 less than or equal to 0.05, which is the equivalent of W minus 32 greater than or equal to negative 0.05. So as a compound inequality, I could write W minus 32 in the middle, less than or equal to 0.05. And over here, W minus 32 is going to be greater than or equal to negative 0.05. And how would I solve this? Well, I would add 32 in 3 places. What is the result? Back here, this is what we talked about. So there's a really good application of absolute value inequalities. Hope you guys have a great day.